So in the last class, what we have discussed, natural radioactivity, where alpha, beta, and gamma radiation were ejected from a radioactive nuclei or heavy nucleus. Today we will discuss one more radioactive process, that is called nuclear fission, in which a heavy nucleus splits up into intermediate fragments when it is bombarded by either alpha or particle or proton or neutron. So now we are going to discuss neutron induced reaction. Okay. So when neutron bombarded with a heavy nuclei, what happens to this nuclei? So that is what we will discuss here. It is a nuclear reaction. Nuclear fission is a nuclear reaction in which a heavy nuclei splits up into two intermediate fragments, whose mass is not less, not low, not small, not big. So intermediate mass fragments, and emit neutrons and large amount of energy. So this is what happens in nuclear fission reaction. Okay, so it breaks down. See, heavy nucleus breaks up into two intermediate fragments and produces neutrons and large amount of energy. Let us take an example of nuclear fission reactions where this uranium, when bombarded by a neutron, initially it forms a compound nucleus. It was captured. So here N 235 plus 1, it becomes, actually it is 236, sorry, it becomes 236 uranium 92 236. So, and since it is not a stable nucleus, it is not stable, which is not a stable nucleus, okay, stable nucleus, it splits up into barium and krypton. Okay, so along with barium and krypton, barium 141 and krypton 92 nuclei, 3 neutrons and 200 mega electron volts of energy will be released. Okay, so this is one nuclear fission reaction. You can see the picture here. So where neutron is bombarded by uranium 92 235, so we can produce uranium 92 236, and later, since it is unstable, it splits up into barium 141, krypton 92, 3 neutrons and large amount of energy produced. Okay, you can see the next two reactions, example number 2 and 3, where the same reaction, the uranium 235 is bombarded by this neutron, initially forms compound nucleus, and later it splits up into Sb133, Nb99, and 4 neutrons are produced along with certain energy, large amount of energy Q, around 200 mega electron volts of energy produced. Here, the third reaction, where same neutron is bombarding this uranium 235 compound nucleus, it is unstable, and later it splits up into xenons and strontium, xenon 140 and strontium 94, 2 neutrons and large amount of energy released. Okay. In the first reaction we got 3 neutrons, in the second we got 4 neutrons, and in the third reaction we got 2 neutrons. Okay. So generally these 3 types of reaction takes place, not only 3, so there are a few other reactions also takes place. It depends on the which reaction is preferred, depends on the energy of the neutron. Okay. So here next see some points here. Whatever the fragments we got, these are called fragments. So these are not stable, these are still radioactive. When they are radioactive, they can emit alpha, beta and gamma radiation continuously. That is one until they get stability, they become stable. So here the products are radioactive. So these products are radioactive. So these end products, xenon 140 and strontium 94 are radioactive. So still they are radioactive, so they undergo beta decay. They emit these beta particles, nothing but electrons, continuously to achieve stable end products. Once the end products are stable, the reaction stops. Okay. So, the next, what about the energy released in a nuclear reaction? Energy released about 200 mega electron volts. So let us take whether the energy is about 200 MeV or not. So we'll check with an example. Let us take an example of a nuclei with a mass number 240. So let this nuclei was broken into two equal fragments 120 and 120. Let us see what is the binding energy of a nuclei with mass number 240. So from the binding energy curve, you can see the binding energy for previous slides. Uh, it is clear that the binding energy per nucleon of a nuclei with mass number 240 is 7.6 mega electron volts. But what is the binding energy for a nuclei with a mass number uh, uh, 120 is 8.5 mega electron volts. When the size decreased, the binding energy of the nucleus increased. So it is increased by 0.9 mega electron volts. 0.9 mega electron volts. Therefore, this is actually gain. Therefore, the gain in the binding energy. This is 0.9 is the gain in the binding energy per nucleon. How many nucleons are there? 240 nucleons. Therefore, the total binding energy, total gain in the binding energy is about 216 mega electron volts. Okay, this is about 200 mega electron volts. This much of energy will be released when nucleus breaks into two equal fragments. Okay, so we can use this energy to produce electricity and to make atomic bombs. So how to use this energy to produce electricity and how to make atomic bombs. So we'll discuss. Next, we saw three fission reactions. In the first reaction, we got three neutrons. In the second reaction, we got two neutrons. In the third reaction, we got four neutrons. Actually, second reaction, we got four neutrons. In the third reaction, we got two neutrons. On an average, in the fission of uranium-235, we'll get 2.5 neutrons are ejected or emitted per fission. When one nuclei fissile, around average 2.5 neutrons eject out. Okay, so and this nuclear fission occurs only due to slow neutrons. Okay, so when a fast neutron, let us see here, when you see it is a slow neutron or thermal neutron. When a fast neutron bombarding the uranium nucleus, it cannot fissile, it cannot produce two fragments. So this fast neutron, when fast neutron bombarded this uranium, it takes the uranium-235 to excited state. Okay, it takes to excited state. It takes the uranium 236 to excited state, and this excited comes to ground state by ejecting gamma radiation. Okay, but this fission reaction do not take place with the fast neutrons. Okay, so reasons behind your knowledge. So I'm not going to discuss why it does not why the fast neutron does not fissile. Okay, so generally it occurs. It experimentally verified that fission reaction takes place due to only slow neutrons. The probability with the fast neutrons is very small. Okay, with the fast neutrons is very small. So fission fragments are unstable and emit neutrons. Sometimes fission fragments are unstable and emit neutrons. Some time after fission, these neutrons are called delayed neutrons. Okay, so here, so whatever the neutrons we got here, these are called these neutrons are called prompt neutrons. These neutrons, 3, 4, 2, 1 neutrons are prompt neutrons. Whenever the fission takes place, so these neutrons are produced. But there are other neutrons also produced in the reaction. Those are called delayed neutrons. not slow neutrons. Slow neutrons are prompt neutrons. Delay neutrons are produced when these fragments, undergo beta decay. Okay, so few other neutrons also produced. They are called delay neutrons. Okay, the delay neutrons plays an important role in the chain reactions. So we'll discuss that. So next, what is a chain reaction? So the process of so here, actually nuclear reaction is a chain reaction, the process of continuation of nuclear fission. So which one once started continues spontaneously without the supply of additional neutrons from outside is known as chain reactions. You can see the chain reaction here. There is one neutron, so you can see this neutron. Okay, this is a neutron. Okay, so when bombarding this uranium-235 produces uranium-236. The uranium-236, it is unstable, splits up into barium and krypton, produces 3 neutrons here. You can see first reaction, when splits up into barium and krypton, produces 3 neutrons. Okay, this each neutron again collide, bombarding this uranium-235 again. Okay, produces 3 more neutrons here, 3 more neutrons. So each neutron again produces 3 neutrons, 3 neutrons here, 3 neutrons. Okay, multiply here. The neutron number is multiplying 3 square, 3 into 3 here, 9 into 3 again 27. So the reaction multiplies. So this is called chain reaction. Okay, the process once started cannot be controlled. So this is a chain reaction. Okay, so here no need to, once you supply a single neutron, okay, to one nucleus, no need to supply continuously. Okay, why? Because 3 neutrons are already produced here. These neutrons can induce another 3 fission reactions. So these 3 fission reactions can induce further 9 fission reactions and 27 fission reactions, 84 fission reactions, etc. Okay, this is called chain reaction. Okay, here so whether chain reaction is controlled or uncontrolled can be decided by using this multiplication factor. This is a multiplication factor. So it is the product. Multiplication factor represented by K. It is the ratio of a number of neutrons in a particular generation to the number of neutrons in the preceding generation. Okay, let us see the previous example. So here it is the ratio of number of neutrons in the particular generation to the number of neutrons in the preceding generation. Okay, so here see this reaction. How many neutrons in this particular generation? How many neutrons are there in this particular generation? 1, 2, 3, 1, 2, 3, 1, 2, 3, 9 neutrons divided by this 3 neutron. Okay, 9 by 3 is equals to 3. Okay, so this generation, it is a ratio of number of neutrons in the particular generation 9 to the previous generation 3. So known as multiplication factor. Okay, if 9 by 3 is equals to 3, so reaction is multiplied by 3 times every fission reaction. Okay, so if this K, if the multiplication factor, if you keep the multiplication factor less than 1, no, it is 3. Okay, if you keep the multiplication factor less than 1, the chain reaction cannot be sustained. After some time, so the reaction stops. The number of reaction, the number of fission reactions will stop after some time. So this type of state is known as subcritical state. So reaction after some time will become reaction cannot be maintained here. Okay, so here chain reaction. Okay, here K is equals to 1. When K is equals to 1, chain reaction is maintained at a steady rate. then every stage, if you are able to maintain only 3 neutrons. In the previous case, we saw that if you provide 1 neutron, it is multiplied by 3 times, 3 to 9 times, 9 to 27 times. Okay. Somehow, if you maintain only 3 neutrons in any generation, so this is called a controlled chain reaction, and which takes place in a nuclear reactors to produce electricity. Okay. K is less than 1. If K is less than 1, nuclear reaction, the reaction rate decreases, so fission starts. If you maintain K is equals to 1, the reaction takes place at a steady rate. Okay. So used in nuclear reactors. This type of condition is known as critical state. If K is greater than 1, the chain reaction becomes self-sustained and leads to atomic bomb. So we cannot control if K is greater than 1. So what happens? So continuously the number of fission reaction multiplied, and we cannot stop this chain reaction. Energy goes on increasing and it will be broken. So this type of reactions are used in atomic bomb. Okay, this type of state is known as supercritical state. Okay, which are very useful to construct nuclear reactors. Now we'll discuss what is a nuclear reactors. Okay, so see here. So what is a nuclear reactor? So nuclear reactors are used to generate nuclear energy through controlled chain reactions. Okay, nuclear reactors are used to produce electricity through controlled nuclear fission reaction, which is and the important parts. See, the important parts of this nuclear reactor are fuel, moderator, control rods, coolant, and protective shielding. See here, this is the schematic diagram. So I'll come to this part later. Now I'll go to next points. First we'll discuss the different parts of this nuclear reactor one by one. The common fuels used in the nuclear reactor are uranium-238, uranium-235, plutonium-230, this plutonium-239 actually, plutonium-239, okay, thorium-232. These are the common used fuels in the nuclear reactors. Okay. See here. So actually, in the mines, here we find some rocks. So these rocks contain a uranium. So it is a compound. This uranium compound contains uranium-235 and uranium-238. Okay. In mines, we will get this type of rocks, and this rocks contains a compound of uranium. In this uranium, we have 230. Uranium-235 is about 0.7%, and the rest of remaining is about 238. About 99%, 99.3% of uranium-238, and we will find just 0.7% of uranium-235 and 99.3% of uranium-238 in this compound. So mined from so this is from the compound. Okay, so you can, out of these two elements, this uranium-235 is fissile material, and when it is bombarded with neutrons, then it can fissile. It can produce intermediate fragments, but it cannot produce. It cannot fissile with the slow neutrons. Okay, it can fissile with the fast neutrons. Uranium-238 fissile with fast neutrons. Uranium-235 fissile with the slow neutrons. That is the difference. Okay. So here, so uranium-238, 238, plutonium, and thorium. These are the commonly used radioactive materials to generate electricity. So next, moderators. So these are used to slow down fast-moving neutrons in the fission reactions. Okay. So here, when the reaction takes place, uranium splits up into intermediate nuclei. The energy released will be shared by all the nuclei, all the products. So neutron also are moving with some kinetic energies. So when the energy is more than the thermal energy, the energy of neutron is more than the thermal energy. So then thermal energy means the energy of neutron. The neutrons which are at room temperatures are known as thermal neutrons. Okay, if the energy of neutron is more than thermal neutrons, so they cannot produce nuclear fission. Okay, fast moving neutrons cannot produce nuclear fission. Okay, so uranium-238 can fissile with the fast neutrons, but uranium-235 can produce this fission reaction with slow neutrons only. So in order to slow down neutrons, so we use heavy water and graphite. Heavy water is nothing but D2O. H2O is light water. D2O, deuterium oxide, is a heavy water. Light water, nothing but hydrogen oxide. H2O is a light water. Deuterium oxide is a heavy water. And these two are used to slow down fast-moving neutrons. Yes or no? So here, actually, this is the schematic diagram. You can see these can see these fuel rods. So here fuel is placed in these rods, uranium made in like rod pellets. These uranium pellets are placed in these rods. Okay, these uranium rods, and these are surrounded by I think it is not mentioned here. It is the moderators, heavy water. This is a heavy water. The water is surrounding this this fuel rods. So when fast neutrons pass through this water, so their energy reduced. Okay, in this way we can slow down the fast moving neutrons. Okay, and the next one, the next component, a control rods. The function of control rod is to absorb the neutrons. So why? Because we have to maintain the control chain reaction. So what happens when uranium fissile, when one nuclei fissile, 3 neutrons are approximately 2.5 neutrons on an average are produced. 2.5 neutrons are produced. But we have to maintain for example, 2.5 neutrons are produced, but we are providing only 1 neutron. What is the multiplication factor here? 2.5 by 1. So here k is greater than 1. So k is greater than 1. So if the k is greater than 1, we cannot control this chain reaction. It is said to be uncontrolled chain reaction. So we need to, this condition, this must be avoided. This situation to be avoided. You need to avoid this situation. So by using this control rod, it can be the reaction can be controlled by absorbing the extra neutron. Whatever the extra neutrons are there, 1.5 neutrons per fission, are absorbed by using these control rods. These control rods are made of boron, cadmium, steel, etc. Okay, so actually this is the schematic diagram. So these are the control rods. These are the control rods. Whenever you find there is an increase in the number of neutrons, so immediately what will you do? You will deeply insert these control rods into the reactor core. So therefore, the number of neutrons decreases. So in this way, we can maintain steady rate. Okay, reaction rate can be maintained at a steady rate. Okay, so what is the function of this moderator? To slow down the fast moving neutron. What is the function of control rods? To maintain a control chain reaction, we use control rods. Okay, so next these control rods are made of cadmium, boron and steel rods. Okay, so generally we use cadmium and boron. So lightweight materials are used here. Light nuclei are used. So coolant. Next, coolant. So the material which is used to absorb heat generated in the reactor is called coolant. So the coolant, normally used coolants are water and molten. So generally we use water as a coolant. So see this reaction. So here water is here. So here water is sent into this reactor core with the help of a pump. So we will pump water into this reactor core with a high pressure. Okay. So here large amount of energy is released. Why? Because during a fission reaction, 200 mega electron volts of energy will be released. Okay, and this will be absorbed by the surrounding water. So this water gets heated. So and it converted into vapor. That is why we have to pump water, cool water at very high pressures. When you pump the water at very high pressures, so the water evaporates at very high temperatures. That is why still this water comes out in the liquid state only. So and this water comes into the heat exchanger. This is called heat exchanger. This is a heat exchanger, H.E, heat exchanger. So where this pipe is surrounded again by water, cool water. So where the exchange of water takes place, here we will pump in this heat exchanger. The water is at a normal pressure only. So this when the exchange of heat takes place, this water in the heat exchanger convert into vapor and will collect this steam, and the steam is used to rotate the turbines. So and when the turbine rotates, electricity is generated. Okay. Now again, whatever the remaining water again passes through one more heat exchanger and becomes cool, and again repumped into the heat exchanger. This process continuously goes on. Okay. This is about the nuclear reactor. This is actual figure given in the textbook. Okay. So this is the schematic diagram. So what is a nuclear reactor? Nuclear reactor is used to produce electricity through controlled nuclear fission chain reactions, and different parts of nuclear reactor are fuel, moderator, control rods, coolant, and last one I forgot, protective shielding. I did not mention here actually. See here, this is a protective shielding. This is the protective shielding. Protective shielding. Okay. So actually, the number of people will work in the nuclear reactor. So here there are different types of particles. Radioactive particles are produced, alpha particles, beta particles, and neutrons with high energies are emitted from this reactor. So it may affect the person who are working over there. That is why in order to for safety measurements, so here there is a protective shield. The wall is a concrete wall is made with a thickness of about few meters. So and this can protect the person who are working over there. Okay, that is called protective shielding. Okay, these are the different parts of nuclear reactor. Okay, so